Welcome to the deep dive. Our mission here, it's pretty simple, really. We want to short circuit that long path to being genuinely well-informed.
Exactly.
We take these complex, high-stakes topics, and today it's the essential language of global warming and climate science, and we just pull out the vocabulary you need.
The precision vocabulary, the words that make you sound authoritative, rigorous, and, well, instantly fluent.
I like that. Instantly fluent.
Well, that's the goal. This isn't about just, passively reading a dictionary. It's about learning context.
Right.
If you're heading into a critical meeting, or maybe you're writing a high-level academic paper, or even just debating a complex topic with friends, choosing the exact right word, that one word that carries the most academic weight and the correct connotation, that's the difference between an argument that's just adequate and one that's truly commanding.
Absolutely. We are so done with low-impact language. We're here to equip you with the formal, high-impact verbs and nouns that climatologists and policy analysts actually use.
And we're going to get into the weeds with collocations.
Okay, define that for us quickly.
Collocations are just those word pairings that signal true expertise. They just sound right to a native speaker or an expert in the field.
And maybe most importantly, the subtle power of connotation.
Yes. It is a shortcut, really, to linguistic mastery in what is a hugely critical field.
So how are we structuring this today?
I think we can organize it around 3 pillars. First, we'll tackle the precision verbs for describing the physical processes of the planet.
Like how things move and change.
Exactly. Second, the language of scientific certainty and reporting, how we talk about what we know. And then finally, the big ones. The high-impact nouns that define the crisis itself.
And I see you've planned a little detour.
A crucial one. We'll take a detour into the art of connotation, because that's what makes your arguments persuasive, not just factual. So, are you ready to dive into the physics of planetary change?
Let's do it. So let's start at the really fundamental level, the physical world itself. We're talking about these, colossal processes, the movement of oceans, the shrinking and swelling of massive ice sheets, the way water transforms from a gas to a liquid.
Right.
When we're describing these huge, continuous, and often really slow changes in nature, simple verbs like move or get bigger just don't cut it. They feel kind of childish.
They do. They lack precision.
So how do we introduce that scientific elegance into our descriptions of movement?
We have to use verbs that communicate duration, consistency, and mechanism. They're just so much more powerful than the casual alternatives like move or melt.
Okay, so where do we start? What's the first one?
The verb flow. It's absolutely foundational when you're describing planetary movement.
Flow.
It means a steady and continuous movement of a liquid or a gas or even an electrical current. Its power is really in that implication of stability and consistency over time.
That steadiness is key, isn't it? If I'm writing an article and I just say, the river moves slowly into the valley, it gives you almost zero sensory detail.
Right, no detail at all.
But if I say, the stream flowed into the valley, I immediately get this sense of continuity, that constant, relentless movement that really defines how water works.
And its most famous application in climate science has to be the great ocean currents.
Of course.
When you're discussing global heat distribution, you absolutely have to be able to use flow correctly. Think about the Gulf Stream.
Right, the big one.
It's not described as a current that, rushes or trickles down. The formal scientific description is a vast, stable current of warm seawater that flows from the tropics northeastwards.
I see the value right away.
Yeah.
If you want to articulate the mechanisms of global heat, that consistency implied by flow is it's non-negotiable. Now, can we apply flow in a different way? Maybe something to do with ice, with the cryosphere?
Oh, absolutely. We also talk about the dynamics of glacial meltwater. So as glaciers warm up, that meltwater has to go somewhere. It has to flow out.
Okay.
But here's a really subtle distinction. When that meltwater flows beneath an ice sheet, it actually acts as a lubricant.
Oh, wow.
And that influences the speed at which the entire massive ice sheet might then slide toward the ocean.
So the stable flow of a pretty small amount of liquid can have these enormous consequences for the much larger, slow-moving ice mass.
That's fascinating, isn't it? A continuous, steady state of movement enabling an entirely different and much larger magnitude of movement.
And just to round this out, for academic use, we often hear flow used abstractly too, right?
Yes, all the time. In policy and finance contexts. If you're analyzing a government's response to climate change, you might talk about the flow of international capital that's been earmarked for climate mitigation projects.
Or the flow of data between different research institutions.
Exactly. In all those cases, flow still implies a continuous, directed stream, whether it's resources or information. It maintains that high-impact connotation of steadiness.
Okay, that's a great start. So from movement, where do we go next?
Next, we have to dive into changes of dimension, of size. And for that, we use the perfect antonyms: expand and contract.
Right. Expand means to become larger. Contract means to become smaller or shorter.
Right.
In basic physics, we usually see these applied to, materials heating up and expanding or cooling down and contracting. But in climate science, we often find the situation that feels really counterintuitive, where both things are happening at the same time across the planet.
And that's the complex rigor we have to be able to convey. It's not a simple story of everything shrinking.
Right.
In any rigorously peer-reviewed paper, you'll read that the Arctic glaciers are contracting. They're becoming smaller because of melting and ice loss.
Okay, that makes sense.
But simultaneously, because of localized weather patterns and in some cases increased precipitation, some Antarctic ice sheets are, surprisingly, expanding in mass balance in certain regions.
That dual action is so essential to capture correctly. It shows you understand the nuance that the cryosphere's response to warming is complex and regional, not, monolithic.
Exactly. If you just go around saying all the ice is melting, you sound like you lack that rigor.
It's too simplistic.
And we can't forget the oceans themselves. Thermal expansion is one of the primary drivers of sea level rise, totally independent of any melting ice.
Explain that a bit more.
As the water in the ocean warms, the molecules just take up more space, they get more energetic. And we describe this phenomenon by stating that the seawater expands in volume as its temperature rises. This is the definition of rigorous application, using expand to describe a thermodynamic change, not just a physical one.
Okay, let's push the boundaries of these words a bit. If I'm not talking about ice, but about, say, economic capacity, how do I apply them correctly?
Oh, that's where those collocations become so useful. Expand is used very powerfully in abstract contexts. You don't just expand physically.
Right.
You expand capacity to process data, you expand a research facility, or you discuss how global GDP expanded by 4% last quarter. It always implies an increase in scale or scope.
And contract. Outside of glaciers, the first thing that comes to my mind is physiology.
Precisely. Contract is very common in biology funds. Muscles contract rhythmically, it's also common in finance, to describe a recession where the economy contracts.
So the common thread is that decrease in size or duration or scope.
That's it. And the academic strength of these words is their ability to shift so seamlessly from describing microscopic thermal expansion to continental ice sheets to the global economy, all without losing their precise meaning.
Okay, so we've done movement with flow and size with expand and contract. What about a change of state?
For state, we have condense.
I think most people probably know this means a gas turns into a liquid, but how do we elevate its use beyond, what we learned in high school chemistry?
Well, condense is the specific mechanism for that phase change, when a gas or a vapor changes into a liquid. The elevated use comes from understanding the conditions under which this happens and, crucially, the consequences.
Okay, give me an example. If I'm writing about atmospheric science, for instance.
You must use it to describe cloud formation. The formal sentence is, water vapor condenses to form clouds as the air rises and cools.
But what's the deeper mechanism that condense implies that a simpler phrase like cool down just misses?
It implies a loss of energy, what scientists call latent heat release, and the need for something called a nucleation site.
A nucleation site.
A tiny particle for the water to form around. Saying the air cooled and got wet is, well, it just doesn't work in a serious paper. Condense describes that critical moment of transition, often happening around tiny aerosol particles, the condensation nuclei. So we can say that pollutant particles act as sites where water vapor condenses into droplets.
Ah, and that connects it directly to climate change and pollution, doesn't it? If we have more particulate matter in the atmosphere from burning fossil fuels, those particles are changing the dynamics of how vapor condenses.
They absolutely are. And think about an industrial application. Carbon capture technology, for instance. It doesn't just cool the gas.
Right.
Specialized systems work to force CO2 vapor to condense into a liquid form so it can be stored or transported. Using condense instantly signals that you understand the physical chemistry involved in these really complex atmospheric or engineering processes.
So using condense instead of, say, change phase or get ret is the fast track to sounding like you grasp the fundamental physics of the system. It's about being specific about that physical transition itself.
Yeah, got it.
Okay, so that covers the language of the physical world. Now let's pivot to the human layer of this. How do scientists and policymakers talk about what they know, what they suspect, and what they're forecasting? This feels like a minefield.
It can be. Academic rigor in this domain is all about signaling your confidence level. In high-stakes reporting, you simply cannot afford to mix up a claim of certainty with a rough approximation.
So these next verbs are all about communicating authority or caution.
Exactly. And the iterative nature of scientific discovery.
So where do we start? What's the word for absolute certainty?
The anchor of certainty is the verb state. To state something is to say or write it in a formal or definite way. It's a verb that you reserve for official positions, for facts that are supported by data, or for institutional pronouncements. It carries weight, and it requires backing.
I find myself using it when I'm citing really foundational material. For instance, I might write, the IPCC report clearly states the 95% confidence interval for projected sea level rise. By using state, I'm positioning myself as someone who is transmitting established, serious, peer-reviewed information.
And that's the perfect use for it. Contrast that with, say, or claim. If you write, my colleague claims the data is flawed, that immediately implies doubt.
Right, it's just their opinion.
But if you write, the lead researcher stated the methodology was sound, that signals the information is verifiable and definitive, at least within the scope of that report.
But where's the boundary on that? If I, as a researcher, state my opinion in a paper I'm writing, does that still carry the same authority? Or is state only reserved for these formal entities or confirmed data points?
That is a brilliant and critical distinction. State typically requires the presence of evidence or that institutional formality. You might state a conclusion that is directly derived from your data, but you wouldn't typically state an untested hypothesis.
So for a hypothesis, I might use a different word.
You might assert it or propose it. For example, the CEO stated the company's new climate goals. That works because the CEO is speaking for the entire institution.
I see.
But if a dissenting employee argues those goals are too weak, they assert their counterpoint. State demands that formal verification or an institutional mandate.
So using state carelessly to describe, I don't know, a casual blog post, it actually weakens the power of the verb for when you really need it, when you're citing a major government report.
It's all about preserving the verb's authority.
Okay, so from certainty, let's move into the future. What happens when we look forward?
When we look forward, we move on to a spectrum of foresight. And here, the verbs predict and estimate define the range between high confidence and necessary approximation.
Okay, let's break that down. Predict seems to imply a degree of certainty that's based on some kind of proven model. It suggests foresight. If I predict that a certain region will experience drought, I'm basing that on validated meteorological models and historical data sets.
And this is where we really see that iterative nature of science play out. Predict implies a model that is capable of generating a specific outcome. Think about short-term weather forecasting. Meteorologists predict rain tomorrow with 80% accuracy.
Whereas estimate carries an inherent uncertainty. It's acknowledging a lack of precise measurement, or maybe the complexity of all the variables. It means to make an approximate judgment or calculation.
Let's consider the challenge of long-term climate modeling. Historically, some early, less sophisticated climate models might have predicted a 2-meter global sea level rise by the year 2100. That word predicted implies a high confidence in the output of that specific model run.
But science changes.
Of course, as new data points come in, say, more accurate measurements of ice sheet stability, scientists realize there are inherent uncertainties they hadn't accounted for. So the revision then states that based on the new constraints, they now estimate the rise will be 1 meter, with a possible range between 0.8 and 1.2 meters.
Wow. The verb choice shifts from predict forecasting a single outcome with certainty to estimate calculating an approximate value within a range. That single choice of verb tells the listener everything they need to know about the current confidence level in the scientific community.
And this leads perfectly to the utility of prefixes. This is a real superpower for advanced vocabulary users. We use the prefix antonyms over and under to immediately critique or quantify a projections flaw.
This is instantly precise. I can take the word estimate and create overestimate or underestimate.
Precisely. If a government report relies on really optimistic economic growth models, critics might argue that the report overestimated the amount of carbon that could be sequestered by new forests.
Meaning the calculated value is too high.
Right. And simultaneously, that same report might have understated the cost of infrastructure damage from coastal flooding.
Meaning they reported the consequence as less severe than it will actually be.
You've got it.
The elegance here is that you don't need a clunky phrase like, they reported a value that was much larger than the actual expected result. You use overestimate. It's concise, it's authoritative, and it carries that implication that the projection was faulty, probably due to some kind of bias or error.
Let's push this nuance a little further. Does using overstate or understate inherently imply that the previous study was, intentionally misleading?
That is a critical question for academic writing.
It is.
And I'd say that while overstate can definitely be used rhetorically to imply a bias, its core academic meaning is simply an error in magnitude.
Right.
In a formal paper, you would follow up and say, the previous model overstated the temperature anomaly, likely due to an incomplete representation of cloud feedback mechanisms. You're attributing the error to the mechanism, not necessarily to malicious intent.
So the word itself just signals the faulty magnitude, not necessarily the motive behind it.
Exactly.
Beyond magnitude, the ability to rapidly form negative meanings using prefixes like un, in, ill, I, and dis is fundamental to constructing nuanced arguments in any field. But it's especially important in debates over scientific consensus.
These prefixes let us express negation or contradiction with extreme efficiency, which is just vital in a field that is so rife with disagreement.
And we constantly see this in policy discourse. For example, nations frequently disagree over binding targets for emissions reduction. They are fundamentally not in agreement. That simple prefix captures the political division quickly and cleanly.
And when you're analyzing data, these are indispensable. If a dataset doesn't align with prior results, we call that data inconsistent. That's so much stronger than just saying the data doesn't match. Inconsistent implies a lack of internal coherence, a lack of reliability.
The practical tool here is recognizing the power these prefixes give you to critique an idea. If a proposed solution requires massive spending but doesn't show clear returns, it might be deemed unnecessary or perhaps impractical.
Right. Or conversely, if a policy is viewed as unfair, it is inequitable. Knowing that in and uncreate these precise antonyms allows you to pivot and critique on a dime.
And it extends beyond critique, too. Think about relational prefixes. Call or kana implies coming together like in connect or condense.
And ex implies moving apart like exclude or expel.
Absolutely. In data analysis, you might collect data, bringing it all together. But to get a specific insight, you might need to disaggregate the reports, breaking them apart by region or demographic, using that prefix dispate to reverse the action of aggregation.
So mastering these small linguistic components gives you huge leverage in an intellectual debate.
It really does. If you can state that an argument is inconsistent with the latest findings, you are making a clear, critical point using the highest level of academic language.